Welcome to today's webinar, Electrical Safety Testing 102. This is a follow-up webinar to our previous webinar, Electrical Safety Testing 101. And it's a series of webinars that we do throughout the year and a continuation of things that we build up on, starting with the simplest things about shock hazards versus all the way to line leakage or leakage current testing. In this webinar, we'll be discussing a few things about how tests are being performed on your product. We're also going to be looking over some safety standards guide and reviewing some of the standards guide. But before we get started, I'd like to introduce our team. I'm Bishan Patel. I'm the presenter for the webinar. I work as an applications engineer here at Associated Research. Also have Anthony Arroyo. He's also an applications engineer, a colleague of mine, and he's going to be the panelist for today. And then we have Brittany Socha. She's going to be an organizer for the webinar. Before we get started, some notes for this webinar. There is a question and answer utility that you could utilize. Anthony's going to be answering questions live during the webinar. If you have any questions about the material that's being presented, use the question and answer utility to ask questions to Anthony, who will be replying live. If you have questions about issues with either the audio or visuals, please use the chat box to ask a question to Brittany, and Brittany should be helping you get through any issues you might have with the audio or visual part of it. These webinars are recorded and they're available on our website within a few days. And if you also like to have a copy of this presentation, the PowerPoint presentation, you can send an email to Brittany at her email address is brittany.socha@arisafety.com, and we'll be glad to send you a copy of this presentation. For today's webinar, like I mentioned earlier, we're going to be looking at some safety tests, electrical safety tests that are commonly required to be performed. If you have products that are agency listed, either it be UL listed or CE listed, there's some types of tests that you have to perform. And we're going to be doing an overview of most of the commonly performed electrical safety tests. We're going to also be looking at what kind of test requirements are called out for in these standards. The standards call out for a specific amount of voltage to be applied, or a specific amount of leakage current to be seen by the product. Or it could be for ground bond testing, it could be an amount of current that needs to pass through your ground circuit. These are the kind of requirements that come straight from the standards, and we'll be taking a look at what numbers are important when we're running these kind of tests. We do also have a safety standards guide or standards reference guide that we publish. In this is a short version of what we take out from the standards that relate to electrical safety testing on your product. So we take out information that relates to the parameters that needs to be used. We'll take out parameters. We'll list out parameters that are basically important for running this electrical safety tests. We'll also, in the standards guide, we'll also kind of list out what instruments are available to use. You could use a variety of AR instruments to perform your electrical safety testing needs. And lastly, we'll cover some of the things not to do when you're testing. In our experience, we noticed that when we're doing factory visits or when we're doing site visit at customers' sites, we noticed some of the unsafe way of performing high-pot tests. We'll also notice that sometimes the tests are not being performed properly. So these are kind of things that we'll go over on what to look out for. Before we get started, I'd like to categorize a few types of tests that may be performed. So there's a test called a type test, and there's a test called a routine test. In type test, this is usually happening when the product is still being designed. Engineering level products or products that need to go to safety agency testing, these are type testing. And in the standards, everything that's mentioned in the standards is mostly related to the type testing. Now the standards may also call out for routine tests. Now routine tests are usually done for production. Any test that ships out from your facility will fall under the routine test. So the standards will usually call out for testing 100% of your product that you ship out. And basically there's two categorization, which is type testing and routine test or production test. Quickly taking a look at what type testing means. When we're talking about type testing, again, it's conducted on engineering level products. They're still being designed. You're still designing a product to make sure is working properly and is electrically sound and safe. Now, when you're designing the product, the standards will ask you to run a particular number of tests, and some of the tests call out for electrical safety testing. And in these tests is where you're making sure that the insulation that you have protecting the end user from shocks or electrical shocks is there and is able to handle a particular amount of voltage that it might see in the life cycle of the product. Usually it is performed by the manufacturer and also safety agencies. So when you send your product in for preliminary testing, if you send your prototype to an agency for being tested, they'll run also the same type of electrical safety tests that are listed in the standard. So manufacturers could perform these, and also the safety agency will perform testing on your engineering products. Now, these are designed to ensure product safety. This safety is also about end user safety and not being able to cause any shock hazard when the products are out in the field. These types of tests are checking for integrity of the insulation. So you have a product that's going to use line voltage. Normally the line voltage is powering up your DOT, and you want to make sure none of the current that's used by the product is passed on to the surface of the product, or if there's a fault condition that were to happen inside your product, it doesn't cause any kind of live dangerous situation where a shock hazard could happen. So these are the things you're checking to make sure during your type testing to ensure that in an event that a fault were to happen inside of a device, a short circuit that may happen in your device doesn't endanger the end user. It is a more rigorous test where a lot more time is called out when you're running a type test. The type test usually call out for a 60-second test, which is a longer duration to make sure your installation holds up good compared to some of the other tests that you will see that call out for a short amount of time. When you're doing routine tests, again, routine test is production line testing. You have designed your product, you send it into the safety agency has approved your product to be electrically safe. Now, that's your engineering product. Now, when you're going into production, there's a lot of variables that could happen. When all these variables come into play, you want to make sure that before you ship out the product is electrically safe. So what do you have to do is you follow the guidance provided in the standards, usually called out by the routine test or production line test. And in this the section of the standards will actually call out to say, make sure every product that leaves the facility is tested. So 100% of the products needs to be tested. It's designed to make sure, again, end user safety is in mind. We want to make sure that every product that you ship is electrically safe and doesn't pose a shock hazard to the end user. Now, the most commonly performed electrical safety test would be the ground continuity and the dielectrical withstand test, also known as a high-pot test. High-pot test is basically a high potential test that's applied to your line or current carrying conductors to ensure all the insulation that's provided between the current carrying conductors to ground is sufficient enough to not cause any shock hazard. Again, these routine tests, we've seen them performed at end of line, meaning the unit could be being boxed up and they're performing high-pot tests while the unit is boxed up, or right before being boxed up to be shipped out. You want to check to make sure the unit is electrically safe. These tests are also required to perform by manufacturers, and to make sure the testing you did when this was an engineering level product still conforms to the same standards. So if you were running your test, if you're running a type test and you ran it for a particular amount of voltage, the standards also ask you to run a similar type of test during a routine test. So that was the difference between a categorization between a class or a type test and a routine test. And now we'll talk about the electrical safety test itself. So like I mentioned earlier, we have a ground continuity is one of the tests that the standards would ask you to run on all your products. There's also the AC high-pot test and the DC high-pot test, are also known as the AC dielectrical withstand test. Another test is the ground bond test. You want to ensure that the ground circuit that you have that ships on your product is sufficiently able to carry current in the event of a fault that could happen. We also have the IR test, is also known as the insulation resistant test. This is spelled out by some of the standards to run an IR test after some of the HiPod tests are being ran, just to ensure that you running the HiPod test doesn't endanger the insulation. So if you have a HiPod test ran, IR test kind of confirms to make sure there's no further damage to the insulation. Some of the other tests, also known as touch current or leakage current testing, applies mostly to medical industry or medical device testing, and this is a standard that will call out for any kind of leakage current test while the device is powered up. The biggest difference between all the other tests and the leakage current test is that the device is actually powering up in a normal condition, and we're checking to see if any current that could make it to the surface of the product while the device is powered on. And we'll discuss this in detail throughout this webinar. We do have a poll question here just to get an understanding of what kind of situation you might have that you run into for the electrical safety test. And we want to find out if you have any difficulties performing any of this aforementioned electrical safety tests. So I'll have Brittany open up the poll and give you a few seconds to fill out the poll.
Hey, Bashan. It looks like 18% said ground continuity, 55% said AC/DC high pot, 14% said ground bond, 18% said insulation resistance, and 27% said leakage current.
Okay. All right. Thanks for your help, and thanks for filling out the poll. So it does look like some of the AC/DC high pot tests is one of the biggest obstacle that you might face to perform. So let's take a look at, we're going to go in order here. So we're going to check and see, talk about continuity first here. So when we're talking about ground continuity, this is what one of the standards says to check on your products. If you're doing ground continuity, you're checking to make sure the path is there for the ground circuit. If there was an event or fault were to happen, the ground continuity is kind of verifying the ground connection is there. So it basically verifies connection between two exposed conductor. And if you had a class 2 product that doesn't have a ground, you don't need to run a ground continuity test. You're exempt from running a ground continuity test. For class 1 products, going back to our previous webinar, class 1 products do actually have a ground pin, and that ground pin ensures that you have a connection to ground. And the product itself may have some type of metal accessible part. So the standards may define anything that a person could come in contact with as metal accessible part. At that point, class 1 products have a ground pin to ensure there's no potential shock hazards. Now, this ground continuity is more of a low current test, just to check for continuous path. It doesn't tell you anything about what kind of the ground circuit, what kind of current it could handle, and that's where we come in with the ground bond test. So the ground bond test is a step up from what a ground continuity is. So not only we're verifying there's a continuous path for ground, we're also ensuring that it's able to handle some type of current. So the ground bond actually verifies the integrity of your ground circuit. If you had product that were designed and tested in your lab environment, and you tested for ground bond, and let's say you run a 60-second ground bond test. Now, in production line, when you get to production, you're producing a few number of products, and then someone forgets to connect the ground circuit. If they forget to connect the ground circuit, then you could catch it with a ground continuity check that somebody didn't connect the ground wire to the chassis of the product. But just making that connection doesn't check to see if the wire itself was good enough to handle the current. So what we do with the ground bond test is to inject high currents and these are usually specified in the standards to be twice the rating of the fuse. If you have a 5 amp fuse on your product, then they recommend 10 amps, or it could be higher of the two of either the branch circuit. So if your product is normally hooked up to a 15 amp branch circuit, they'll require you to run a 30 amp ground bond test. Now, when you run a 30 amp ground bond test, you're checking to see if the current through the ground circuit handles 30 amps of current for a quick 1 second during production testing, or it could be 60 seconds during type testing or prototype testing, to make sure that ground wire that you bought for this device or this product is capable of handling the current levels that it might see. If it was a household product, I plug up the product in my house, and if your device short-circuited, there's a potential that it could see more than 15 amps of current, and that's what we're making sure that the ground wire doesn't open up when it has a fault condition. Usually, basically, it's a low voltage, high current test. The standards will specify what type of voltage to use in your product for your ground bond test, and the standards we usually deal with specify voltages of less than 12 volts. So again, ground continuity is a low current test, and then ground bond is a high current, checking the integrity of the ground circuit. So taking a look at the circuit diagram of what we're actually doing. So on this diagram right here, we have your product, the device under test, which is on the right side here, and this is a class 1 product, so it has the ground pin, and the ground pin indicates that there's some type of metal accessible part or metal chassis point or some type of metal on your DUT. If you do have a ground pin, what we're going to do for a ground bond test is use a ground bond tester, the image showed on the left side, to inject high current onto the ground pin. So the ground pin is on your line core, we're injecting high current there. That ground wire goes all the way to your chassis of your product, and this wire has some type of resistance. So once we're injecting about 30 amps of current or 15 or 25 amps of current, we want to make sure the resistance of this wire doesn't go above a particular value. So the standards will specify what value this needs to be. On a pass condition, what happens is when we're injecting high current into the ground pin, the resistance of the ground circuit doesn't go above a particular value. The standards may call out for 200 milliohms of resistance, 100 milliohm of resistance. So this is where your numbers come into play when you're looking at standards. The standard is going to say run a ground bond test at twice the rated voltage of your fuse or the branch circuit, and make sure the ground is capable of handling the ground current that it may experience. If you were to have a fail, it could mean one of the two things. Either there's no ground wire, that the current is there's an open circuit, that could be a failure. Another failure could be where you have too much resistance. So the standards is calling out for 150 milliohms of resistance. At that point, if you go over that amount, the tester is going to fail out the product saying, I read more than 200 milliohms of current. This is not a good ground circuit, or doesn't specify to a particular standard. If we were to take a look at how the test is performed, we have one of our HiPod Ultras here, and that could perform a ground bond test along with HiPod test and IR test and also continuity test. What we do, we're using an adapter box here to simplify the image here. So when we're plugging in the product, it's a class 1 product with three-pin line cord that plugs into the adapter box here, and we're injecting high current using the red high current leads, and the returns measured onto the chassis or metal point of the product. So this is a toaster that has a ground pin and also has a metal accessible part, and we're checking to see that there's a continuous path. First of all, there's a continuous path through and through, but also that it could carry the amount of current that's specified in the standard. Again, the unit will display the current that we're passing through the circuit along with the ohmic resistance of the ground circuit. Standards will call out for less than 200 milliohms, 150 milliohms, depending on what standard you're trying to qualify to. Now we are measuring impedance of the ground circuit. There's some standards that call out for the voltage drop, which using the Ohm's law, which will be just V equals IR, you're able to calculate the voltage drop. So if you have standards that call out for just a voltage drop, our instruments, the Hyper series, Hyper Ultra series instrument, does have the capability of displaying the actual voltage drop across the ground circuit. So majority of the standards call out for resistance measurements at a particular current, and then some standards will say, okay, we also need to know the voltage drop across the ground circuit instead of telling you the resistance. At that point, you could use our Hyper Ultra series testers to actually see the voltage drop across your DOT. Few other things about ground mount tests. The parameters vary by standard to standard. So there's not a set parameter that tells you this is what the ground circuit should be or this is how much current you should pass through. For example, when you're looking at IT equipment, the UL standard 60950, it calls out for the current to be twice the rating of a fuse or the branch circuit. So like I mentioned earlier, if you were connecting the IT equipment to a 15 amp breaker, or potentially that IT equipment could be connected to a 15 amp breaker, you want to ensure it could be the 30 amp ground mount test. We make testers up to 60 amp that could do ground mount tests. So a wide variety of testers that we make go up to 60 amps of ground mount testing. You should consult with your safety standards to ensure that you're doing the proper test and proper the numbers you're using are properly used. So if you're using if you're going by the standards and if standards call out for 25 amps of ground mount test during prototype, and then if they're only calling for continuity during production, you want to do at least the continuity test during production and make sure the ground mount test is performed during the type testing. And I had mentioned this earlier about the voltage not exceeding 12 volts. Some standards will say use voltage between 6 volts or 10 volts or less than 8 volts, but majority of them stay within majority of them stay within under 12 volts. Now for prototype testing, which is really important when you have the product in the lab or still being designed, the ground circuit is tested for almost up to 120 seconds. So this is almost 2-minute test, 30 amps of current passing through the ground circuit, ensuring the ground circuit is able to handle the current for a longer time. If in the event that the current was too much for the wires to carry, the wire itself will start heating up, and as soon as it starts heating up, the resistance of the wire is going to keep going up and up until it goes beyond the value specified in the standards. At that point, your test is considered a fail. So, all right. We do have a video, and in this video we're going to be showing you using our Hyper Ultra to perform a ground mount test and a ground continuity test. And let me go ahead and bring that video up here real quick. So you could see in this video here that we have our product connected to it's a fan. Even though the fan is plastic, it has these metal screws, so that's a metal accessible part. It is a class 1 product, so it has a ground pin here due to the fact that it has this metal accessible part. And you see the tester on the right here is our Hyper Ultra. So I'm going to play this video and then talk about the results in a second. When we press test for ground continuity, the first test we run is the ground continuity. So if you could see, it's a 3-second continuity test. It's checking to make sure there's a continuous path from the red high current output to the black return lead. So the path it will be through the red ground pin, and then it comes out to the metal screw here and to our black return lead and goes back. So this is a continuous path. Our meter is reading 0.089 ohms, so 89 milliohms, and this is a good continuous path. But again, this is a low current test. If we were to do the same test, now we're running a ground mount test. At this point, we ran 30 amps of current, and the resistance was still around 87 milliohms of resistance for this ground circuit. So again, we ran the ground continuity test. It gave us a pass, and we ran a ground mount test of 30 amps. The circuit was good enough to have 30 amps go through it and still not break open. Again, the results here, a close-up view of what we just did. For ground mount and ground continuity, only one part of your circuit is being tested, which is the ground circuit. So red high current lead is injecting high current on your ground pin. The returns taken onto the metal screw or metal accessible point or metal chassis point, and at that point you're performing a ground continuity and ground bond test at the same point. If you look at the results here, you had a continuity that passed, a 3-second continuity, and then a ground bond was 30 amp ground bond test that was passed. You could also see the voltage drop. So again, the new testers that allows us to display this the parameter is the voltage drop. So 2.83 volts were dropped across the ground circuit. So again, some standards that do require a ground circuit voltage drop, the newer instruments able to tell you right off the screen itself how much voltage was dropped instead of you having to calculate the voltage. All right, so going on to the next slide. And just to review here, if you were to look at the top here, if you bought a ground wire and the ground wire had a bunch of strands in it, and then at some point in the ground wire there's only one strand connected, that one strand connection will pass a ground continuity test. Why? Because there's a continuous path from one point to the other. Now, if you were to run a ground bond test through the same wire, the wire, if there's only one strand available for all those electrons to flow through it, they're going to heat up the wire and burn it and open it up. At that point, you'll detect a ground bond failure on your product. So I like to use this example where we had a customer that did all their type testing, which is prototype testing, engineering level testing, and they used our equipment and they were passing all their tests. And then 6 months later, we get a call saying, I can't get my product to pass the ground bond test anymore. And he kept telling me there was no changes made to his product, there was no other changes made. And then we finally narrowed it down to the line cord. So basically they had went out and bought the cheapest available line cord that cannot handle the 30 amps of ground bond current and will show more resistance. So the person kept saying that they didn't change anything in their DOT, but they went out and bought the cheapest available line cord, thinking that every line cords are the same. So at that point, he realized his mistake, and they actually went out and bought a similar line cords that they were designed for. So again, these are the kind of things you could check for and catch before it goes out into the real world, and that where it could open up for more damage to either the end user, or getting electrical shock hazards to the end user, or just being a product that's not electrically sound. Moving on to the dielectric withstand test. This is also known as a high path test or high potential test. What we're doing on a high path test, we're making sure that the insulation that's there to prevent anybody coming in contact with the line voltage is sufficient enough for everyday day-to-day uses. Now, when we have a product that they're designed for 120 volts or 230 volts, those are your day-to-day voltage is going to operate at. What happens is there's also voltage transient that could occur. So when they're switching at the utility station, there could be lightning strikes, or it could be some other way of some kind of transient made it onto your line and neutral of your product. At that point, if you design your product to only withstand around 230 volts, when those transients happen, and those transients could be anywhere from 1500 volts, 2000 volts, in that range, when the transients happens, you're kind of creating a shock hazard for the end user. So what the standards came up with is a way to make sure that your line carrying conductors are always isolated or insulated from anybody that could come in contact with the product. Going back to our example of a toaster, if I was around the toaster, I feel safe enough to touch the toaster because there's product or insulation that's protecting me from the line voltage. And the dielectric withstand test or the high path test is ensuring to make we're applying high voltage to ensure that this insulation throughout the life cycle of the product, if it was ever exposed to any high voltage, is still able to withstand that voltage and not break down. So we're deliberately applying high voltage, which is applied to line neutral because they're both line carrying conductors, and then we're checking and we're stressing the insulation from those line carrying conductor or current carrying conductor to ground. At that point, any insulation that falls in between will be tested for high voltage or potential of shorting out or potential for arcing over. um, there's also resulting leakage current that could happen. So if you have an insulation, and the normal insulation just protects you from a direct short, but the insulation's job is to make sure it impedes the flow of electrons. So the insulation would allow some electrons to flow through it, but majority of the electrons are stopped up and not does not flow through the insulation. When some standards call out for a particular results for a HiPAT test, they're either looking for a breakdown. A breakdown is basically a short that happens in your product, or an insulation that's missing insulation and it arcs over to the other side, and this is what causes a bad product to be not electrically safe. When you run a HiPAT test on these products, you're either going to see high amount of leakage current due to the missing of insulation at some point, or you're going to see a direct breakdown which causes a short between two components, or it could be a short between the line current carrying conductor to ground. So again, the HiPAT test is to verify that insulation is able to withstand the high voltage that it may experience during a normal life cycle of the product. If this product is going to be plugged up to a household receptacle, that household receptacle might experience more than 120 volts, at some instance up to 1200 volts. Now the type test is also one of the most commonly, the HiPAT test is one of the most commonly performed electrical safety tests. The nature of this is to ensure everything you've done so far in your production doesn't jeopardize the electrical safetiness of the product. So you perform this at the end of your line when everything is screwed in, the product is ready to go, and there's no chance of anybody opening up the product under test or going inside and changing wires. At that point, you're ready to do a HiPAT test on the unit before you ship it out. You could also detect your design flaws. Imagine that you had product that was designed in a particular way, and during production there's some component that was not placed properly, or their components were placed together too closely. At that point, the HiPAT test will kind of detect either higher leakage or straight up breakdown will show up on a tester, indicating that while in the design phases I was seeing, for example, 3 milliamps of leakage, all of a sudden now I see 8 milliamps of leakage. There's something wrong in production where some components are not being either properly installed, or we're using bad components that are leaking more current than they did when we're testing it. Going back to the ground bond example of the guy that bought wrong line cables, we have also instance of people finding out the capacitors were changed out by their distributors, or people they buy the capacitors from. So they design the product a certain way, they go down to ground, do a production line test. During a HiPAT test, they discover this bad component that was being supplied to them. So again, it's a variety. It is a test that could tell you a lot more than just the installation of a product. You could check for workmanship defects. You could check for creepage and clearance distance that are called out for in the standards, and again, this is probably the main purpose of using a HiPAT test, is to do make sure the insulation is there first, and then the other benefits are the workmanship defects are detected, and also any kind of creepage and clearance distance which you might not be meeting. So let's take a look at the circuit representation of what a HiPAT test looks like. On your left, you have our HiPAT tester, or the Omnia series tester, which is able to do all the electrical safety tests, AC/DC HiPAT tests, IR tests, ground bond tests, along with line leakage tests. But focusing on just the HiPAT test for a moment, you could see that the product on the right, it could be a typical product that has a line neutral and a ground, and ground is normally connected to the chassis of the product. So that's why you see the GND connection is to the chassis and also to the ground circuit of the product. Now, line neutral are usually they have their own little path, and the resistor represents your product. It could be a heating element, it could be an LED, or it could be any number of devices that are represented by the resistor. Now, normally, if you had a good insulation, which is around the flashing green light here, is where all the insulation will fall in. So insulation could be an actual material insulation, or it could be air. Air is the insulation between two products. So you give enough distance between two components, air acts as an insulator up to a certain point. You keep if the components keep coming closer and closer together, you may not pass the high pot test because the air does not act as an insulator anymore because the distance between the components was shortened up. But for this one, taking a look at this high pot test, when you're performing, you're shorting the line and neutral together, and what you create basically is a capacitor. When you create when you have metal on one side, insulation on middle, and then you have a metal on the other side, you're creating a giant capacitor. In this case, one side of our test is the current carrying conductor. It could be any circuit in your product, the insulation that you designed or incorporated in there to protect the product, and then you have your ground circuit. So you created this big capacitor, and there's naturally going to have some leakage current since you created this capacitor. Now, some standards will call out for this leakage current to be less than a particular amount, let's say less than 5 milliamp, for instance. But most of the standards are concerned with breakdown. You want to make sure that any of these line carrying conductors, which is the top line flashing green here in the big square, doesn't short over to the other side. So this is a pass condition. There's not leakage, not enough leakage to hit the high limit, and there's no breakdown happening. If there was a breakdown, or if the leakage was higher, then our instrument will indicate a failure. In this case, what's happening is that we had we have a high pot or high voltage being applied to line neutral of your product, which is a current carrying conductors, and then they either short it to ground or short it through the insulation to ground in some form of manner that it causes a breakdown in your insulation. At this point, a high inrush of current would happen, or high current will be drawn on our instrument, and our instrument will detect a OFL, meaning an overload of circuit, and we're able to detect the breakdown. So in order for a breakdown to happen, it needs to basically act like a direct short when it's trying to draw a lot of current. And then we have sensing circuit that detect arcing. So arcs are happening right before a breakdown happens between two metal products, and the arc usually happens through air or through some kind of material. And when an arc is happening, it creates the high frequency noise um, on your current meter. So when we're detecting this high frequency noise, we're able to tell when a breakdown is happening due to the high frequency noise happening on the current circuit. Now, we go into a lot more detail in our other webinars. So following this webinar, we'll have a series of webinars that go into detail on each and every test. So there's other stuff we covered in our following in the webinars that will follow. They'll go into more details on arcing and breakdowns and all the other limits and everything. So for this right now, we're going to cover basically a pass-fail condition on a high pot test and how to perform a high pot test. So in here, you could see we're using just the line neutral of the fan and connecting to the chassis. So if we have a fan, it's our product under test or device under test, and then it usually has a line neutral which powers up the device. When we're doing a high pot test, we're not concerned with the unit powering up or not. We're just concerned about the insulation property of the product. So we're going to apply high voltage to the components that usually get normal voltage, and we're going to stress the insulation to make sure it's not a direct short to the chassis, or it's not a direct short, or it's not leaking current to ground. Now, there's inherent current to all insulator. Not every insulator is a perfect insulator, but there's a point that comes in a voltage at the insulation is going to start breaking down. So when you go beyond a particular range of voltage that the insulator could handle, you're going to start seeing more and more leakage current due to the voltage that you just applied across the insulation. And there's going to be a point when at that point the insulation is going to break down, and that's known as the breakdown voltage of the insulator. Now, we have some medical device testing customers that run high pot tests at 4,000 volts. So these are dual insulated products. They're making sure it's not any connection to ground, and they're designed in a particular way that it handles 4,000 volts of high pot testing. That's not necessarily true for normal products. So if you had a normal toaster or normal fan, the insulation, the engineering design levels are designed to withstand around 1200 volts of high pot testing. Now the results could be either in the leakage. So when we talk about the insulator leaking some kind of current, we're always talking about leakage to the insulation. And when you're doing a AC high path test, this leakage usually is in milliamps of current. When you're doing a DC leakage current, this is usually in microamps of current. High path test is required for both class 1 and class 2 products. So again, class 1 products has the ground pin. Class 2 products don't have ground pin, but they provide protection by having dual insulation. So imagine you had normal insulation for class 1 product. For class 2 products, now you have dual insulation on top of each other. So it provides protection by using two dual insulation. Plus, it doesn't have any metal accessible part that come in contact with the live circuit of the device under test. Some standards do call out for AC. Most of the standards call out for AC testing. So if you're using your product to power up by the wall outlet, for instance, if the wall outlet is always going to be AC power, they'll request you to run the high path test in AC voltage. There's some standards for like cable manufacturing may allow you to run DC high path test. AC is more strenuous because it's performing in both polarities, and also the AC high path voltage has peak value which is higher than DC voltage. So some standards do allow you to convert from an AC to DC standards, but you have to refer to your standards to make sure if you're not if your product itself, and we've seen this before where the product itself may not work properly under an AC high path test, like heating coil for instance, then we go over to a DC high path test. And some standards allow it, some standards don't. So you would have to refer to your standards to check if the AC to DC conversion is allowed or not. We would like to use a general rule of thumb to figure out what the high path voltage that needs to be applied to your product. So if you have a product that's designed for both 120 volts and 230 volts, it's always the higher voltage. So you don't necessarily say, oh, I'm going to ship it to US, I don't need to test it to the higher voltage. If the product's designed that somebody could actually hook up 230 volts to it, and it's specified on your input label that is 230 volt product, then you want to apply the higher of the two voltages. In that case, twice the rated voltage, which is 2 times 230 or 240, normally is written out at 240, plus 1,000 volts. So 1480 is a good approximation of what the standards call out for high path testing. Again, we're going to apply 1480 volts of voltage in our current carrying circuit to make sure the insulation that's meant to protect it is there, and it's not missing anything, and it's not breaking down to ground or having excessive leakage current. So that covers our AC high path test. Now I'd like to cover IR test, also insulation resistant test. This is exactly same as a DC high path test or DC withstand test, in a manner that the connections are the same. You're still applying high voltage to your line neutral shorted together, and you're measuring the return on the chassis of your product. But the difference here is the voltage is not, they're not the same voltage as your high path test voltage. Normally the standards will specify anywhere from 500 volts to 1,000 volts, but we also have testers that go up to 6,000 volts for IR testing. So if your requirement calls out for insulation test, also known as a meager test, and then allows you to run these kind of tests, meager test, and allows you to run these tests at 500 volts to 1,000 volts. But if you have some that require more than 1,000 volts, we have instrument capable of doing up to a 6,000 volt IR test. Now, when I say it's similar to the DCW test, we're basically making the same measurements. We're applying high voltage, measuring the resulting leakage current. Now, instead of displaying resulting leakage current, we're going to display the actual value of your resistor or your insulation. So if the insulation is good, a good insulation is defined as more than 10 mega ohm of resistance from one side to the other. That's a good insulation. Now, if you go into giga ohm resistance, then that's even a better insulation. So the standards may call out for a minimum of 10 mega ohm of insulation resistance for your product, tested at either 500 volts or 1,000 volts. Now this is actually providing you a quantifiable value of your insulation. Previously we were checking the leakage current. It just shows you how much leakage is happening through your insulation. But for an IR test, now it's specifying or actually displaying you in a quantifiable value of the ohmic resistance of your product. I did mention earlier that when you perform a high path test, even though you have product that's designed for a particular amount of voltage, it may or may not have some missing insulation, and it may not pass your high path test, but when it gets to an IR test, it may go below 10 mega ohm of resistance. At that point, um, that defective product you HIPAA tested, it passed the HIPAA test, but it got to the IR test and it did not meet the minimum requirement by this for the standard. So there's that possibility where a marginally good insulation in your DOT may pass a HIPAA test, and when it gets to an IR test, is below minimum required by the standards. This is also performed for this IR test is also used for the motor, like electrical motors and things like that, to check the integrity of the insulation. So the example I like to use is always where you install a motor in a station or a factory, and then you're checking for the insulation to make sure the insulation of the motor is good. But there's going to come a time when the wear and tear on the motor kind of starts creating these breakdowns in your installation. So if you're doing a yearly test on the motor, a yearly IR test on this motor, you're going to see a sharp drop off in the insulation resistance value. So instead of being 50 mega ohms, it's going to start going down to 40, 20, and all of a sudden you're going to see it go down to 10 or even less, 5 mega ohms. At that point, what it tells you is that this motor has reached the service or reach the end of the life cycle for the insulation part. So either remove the motor, put a new motor in, or service this motor to make sure the insulation is back up and to proper levels. Again, this is not one of the most commonly performed electrical safety tests, but it is a part of the safety test that is required by some standards. If you're looking into standard, the EN standard 60204-1, safety of machinery, it specifies that you do an IR test after your HIPAA test of 500 volt DC IR test, and to make sure that the resistance is not less than 1 mega ohm. This is kind of generous, 1 mega ohm, but we've seen it anywhere from 1, 10, even some require more than 10 mega ohms, 100 mega ohms of resistance. So like you see that the standards could vary on how much resistance is allowed for your insulator, but generally speaking, the higher the resistance is really good for the product's electrical safety, where there's no potential hazard at that point. We do have another demo here of our tester performing the AC HIPAA test, a DC HIPAA test, and also an IR test. So let me really pull that up really quick here. In this test, the parameters are preloaded on here, but what I'm going to show you is with our HIPAA Ultra series of instrument, it does have a touchscreen interface, and Tony was helping me out with this video, so you could see Tony flipping through the parameters to be able to edit the parameters properly. So you have your high limit parameters, low limit parameters, any other parameters that come from the standards, you could set them here. And again, we do have detailed webinars they talk about just particularly HIPAA tests, and then they talk about ground mount tests, and they talk about line leakage tests. So there are our webinars designated for each type of test, and you will get a lot more information in those tests, but this is just a quick overview of what we're doing when we're performing HIPAA tests. So I'm going to pause it really quick before he presses test, and if you take a look down here, we have a high voltage cable coming from our tester. We are using a paper clip just to do a demo, and it's shorting line and neutral together. So you can see the high voltage is being applied to the line and neutral shorted together. I could have easily gone to the ground pin of the product for my return, but I decided to use the chassis point of the product, which was the metal screw on this fan. So if this was my DUT, or this is what I'm in charge of in my production, this fan would need to be tested for HIPAA test, and this is how I would hook it up. We also sell adapter boxes that the adapter could plug directly into the into our instrument without needing for this line neutral to be shorted. But I just wanted to show you an example of what's being tested. You're applying high voltage where normally it's only going to see 120 volts or 230 volts, and you're making sure nothing breaks over to the other side, arcs over to this metal screw, because this metal screw is going to be there for making sure if somebody's able to touch it, they don't get shocked at that metal point. So you want to make sure there's enough insulation around your line neutral that doesn't cause any electrical shock hazard. Again, so in this case, we're going to apply 1240 volts. Our high limit is 5 milliamps. I want to make sure the leakage through this does not go beyond 5 milliamps. So we'll talk about the results. So we did an AC test, a DC test, and basically a DC test is performed in a similar fashion. So no connections are changed out. Only the leakage goes from milliamps to microamps due to the nature of how a capacitor acts in DC voltage versus an AC voltage. Going back to our slide here, I do want to show you the result screen here. We do have an AC pass that showed the real leakage was around 0.2 milliamps of leakage. During the DC, this was the leakage to the insulation. There was hardly any leakage on the DC high pot. And the IR test was ran previously, and the IR test came out to more than 50 gigaohm of resistance. So what that's telling us is that when this line and neutral are shorted and applying 500 volts here, the resistance to ground from that point or to the chassis point here is more than 50 gigaohm. Or is saying on a high pot test, you're looking at if I ever encounter 1200 volts on my line or neutral, my insulation is good enough to not allow any current to flow to the chassis of the product. And you can see it's 0.2 milliamp. And this is a rare scenario where you might have transients on your line voltage. Okay. And on a quickly describe leakage current testing, as later in the year we do have almost 2 full webinars designed for leakage current testing. This is similar to what was also known as touch current testing or enclosure testing. But this is a test where the unit actually powers up, and what I mean by powering up is the device is fully powered on, is in a normal condition, the temperature-wise, and power up. If you had any kind of software that needs to boot up, and then it needs to get into a particular state, you want to get your product into a particular state to perform this leakage current test. Now, in a leakage current test, we have an additional a requirement of having an MD, which is a measuring device. A measuring device kind of simulates what a human body will look like for when it comes in contact with your DOT. So going back to our example of a toaster, if that toaster is a class 1 product that has a ground pin, and if I plug it into the wall, if I go touch the toaster's the control knobs, those are all metal. If those metal knobs are connected anywhere to the circuit, I want to make sure I don't get shocked at that point. So a leakage current test kind of designed to let you know how much leakage current will flow in an event that a ground pin was broken, or somebody didn't wire up the ground properly in your house or something like that, and you go up and touch the toaster. Now the toaster is waiting for a ground, somebody to show ground for the current to leak. So all that current is going to pass to the person, and we're using a measuring device to measure these kind of leakage current. Now, the standards will ask you to run both single fault conditions, which could be an open ground, which is a single fault condition. Imagine somebody broke off a ground pin of your class 1 product, or if the electrician didn't wire up ground properly on an outlet. So if that's a single fault condition. There could be also a condition where the outlet is wired opposite, so line neutral are switched to neutral and line. If you didn't design your product properly, when they plug into the wall neutral line instead of line neutral, if you start leaking more current, the safety center wants to know about it. So we kind of simulate the switching of line neutral for your product to make sure it doesn't leak extra current when somebody's coming in contact with your product. Usually this is ran at 110% of your rated input voltage. So going back to our example, if it's rated for 120 and 230 volts, the standards usually specify 10% of that value. So I've seen products that are rated for 240 volts. You add 10% of the value to it, so 264 is the test voltage that you need to power up your device with and measure this leakage current. This ensures that there's fluctuation in real world, and you're not always going to see 240 or 230. You might see up to 264, which kind of creates more leakage, and that's what the standards are calling out for. It is a commonly performed medical equipment. Manufacturers perform these tests all the time, and again, this is where in medical industry, where you have all these products that come in contact with a human being, you want to ensure that there's no leakage current coming from all these products that are connected to the person. So you want to minimize the amount of leakage current that's sent out towards a human being in case they're not able to get away from the shock hazard, if there was any shock hazard. So that's leakage current testing, and here's a circuit representation of a leakage current testing. This is DUT on the right, and then the tester on the left. We're using the MD to kind of simulate what would happen if they come in contact with the DUT. We're measuring the flow of current back to the transformer that generated the normal voltage for this DUT. How much current is going to leak through the MD? Again, this is to minimize shock hazard while the device is powered up in a normal day-to-day scenario. MDs are specified in each standards, and they're all different. 60601-1 medical equipment standard specifies this particular MD. It has a resistor R1, R2 with a capacitor, and this is to simulate a human body more particularly in a frequency response, where you could have current anywhere from 0 to 1,000 hertz, and it's to make sure that we're not a purely resistive product. We could be capacitive and resistive, and we want to make sure we kind of simulate the human body properly. So the MD is kind of spelled out in each standard properly, and our instruments able to select a proper the MD that you need for your testing requirements. All right, so I'll use this time to have, if you have any questions about the material that I just covered, I do have a few more slides to go over. So if you have any questions, do use the chat box that I could answer general questions over the air. Or if you have any particular questions that you need help with, we could always you could always use our email addresses and email us the questions.
Hey, Bashan.
Yes.
A good topic to talk about with these questions is, while standards will give you the test voltage and the dwell time, how does one identify how to set their ramp or rise time and high limits and low limits?
Sure. So, I mean, I've seen standards that kind of define a ramp time. So 500 volts a second is kind of what's recommended. I actually read some of the standards, and we have access to most of the standards, and the standards will say 500 volts a second to ensure that you're not applying voltage right away. I mean, our instruments will apply voltage within 0.1 second if needed, but it's always good to allow a little time for the voltage to ramp up, especially DC testing. In DC testing, as soon as you apply a lot of voltage to a DC capacitor, it's going to try to draw a lot of current. So at that point, you're going to see a false failure, because it'll fail out saying, I see a failure, but that's not necessarily true failure, because the device, you need to ramp up the voltage properly, let the device charge up the way it needs to. So you might need to allow anywhere from, depending on your product, 5 seconds, 10 seconds, 15 seconds to properly apply that voltage. So that's where the ramp up comes in. Ramp down is another thing to ramp down voltage slowly enough and make sure you're fully discharging the product. Now going back to high and low limits, so if the standards don't specify it, you might want to take a sample of known good products, take a 15 sample product or 20, 30 products, and try to measure the leakage current of the product. So if you get a particular number of leakage measurements for your products, we generally recommend 15% plus or minus of this value to set your high limit and low limit, to kind of narrow it down, saying, if this product was leaking higher than this amount, I need to know about it. Or if the current is not leaking anything at all, I need to know about it. So you kind of like you're kind of like putting them into between these 2 points, and you want to know about anything that exceeds these 2 points. So 15% is a good number. We see in medical industries that go 10% plus or minus of this average leakage, and then we've seen customers that don't use high or low limits at all, and they're just looking for a breakdown. But it's good to use the high-low limits. It could be also 25%. So there's a point where your engineer came in and said, hey, we're getting too many false failure. Just go ahead and open up the window a little bit. 25% is still good enough. If it leaks more than 25% than the normal average value, I need to know about it. If it leaks less than 25%, I need to know why this product is so good. I hope that answers the question.
Yep, I think we're good. You can keep
Okay,
going.
all right. Um, so I know we're kind of coming up against time, but I do want to quickly go over. There's a handout section in your on the right side for GoToWebinar that where we post our standards guide. So we start off with a safety standard guide. I do have 61010 as an example up here, but this is a test and measurement equipment that even our instruments are 61010 qualified. So we have to run high pot test, ground mount test, continuity test, on our instrument, and this is kind of where we get our numbers from. So if you take a look at the impedance of the protective bonding of plug connected equipment, so 6.5.224 is a clause in the standards that kind of tells you run a 25 amp ground bond test, AC or DC, or twice the highest rated current, whichever one is greater. So you want to run it for 60 seconds this should be type testing, 60-second in type testing, and on the right side it kind of tells you what the pass criteria is. So the impedance needs to be less than 100 milliohms between the protective earth circuit and the ground or the chassis point. So again, these are the kind of numbers that we have in our standards guide, and if you need any additional information, we're always available to help you determine which sections you should be using, and we could provide some help in that scenario. I do want to show an example of what the standards guide looks like. So here's the main page of the safety standards guide published by us. Shows you the particular standards that we talk about and how to use the guide, but then it goes into each individual standard. So there's a standard here, and then 60335. I believe that's the household appliances. 60335-1 is dealing with household appliances. So if you're making products that are used in household, you have these requirements that are put forward by the standards for you to perform testing. Further down, you will see 60950, and there's some other ones here. Also 61010. That's what I had up on the slide. And then we have 60601, which is a medical standard for medical industry, a medical equipment manufacturer. And then we have UL 1598 for luminaries, types of tests that are required. So again, we could also post a link in the chat box if you need a copy of this, or also check the handout section of the GoToWebinar. Now, I want to quickly mention things to avoid when you're doing tests. I know we talked about a lot about product safety, but this is more for your operator and testing location or test stations. We want to make sure you're not touching a DUT while the DUT is being tested. Again, it's a high voltage test. It is low current, but the current is enough to be a potential shock hazard to you. ESD smocks are not recommended. ESD are kind of opposite of what we want to be. So you don't want to be grounded when you're doing a high pot test. We want the unit to take all the current and the charge through the insulation. ESD smocks provide a path to ground, which is not desirable. You don't want to touch the test leads during test. That's a common notion, but we've seen where we get requests about people playing around with test leads, not knowing what they could output. So you want to make your operators aware of what potential hazards are here coming out of this tester. As recently as yesterday, we took a call about the operators never reporting a shock hazard, and they were getting shocked, but it was never reported, and they're like, oh, everybody gets zapped at this place. Well, you're not supposed to get zapped when you're performing a high pot test. You're doing something wrong if you're getting shocked performing high pot test. So you want to ensure that your operators know what's going on. Use some of our webinars, use some of our slides to do a class on it to kind of inform them what kind of things to do and not to do during high pot testing. Some of the common stuff is to not make sure you don't break off the pin on test equipment. Again, the ground pin is there for a reason. You do not want to break off the ground pin that could open up for potential shock hazard. And on the left side is a broken ground pin. So you don't want to plug in. If you find something that has a broken ground pin, you probably want to avoid plugging that into the wall and find a replacement cord for it. Here are the things I talked about in more detail. We do have some points that we make here about making sure you know the product, you're testing, making sure the installation you're testing is not overstressed, understressed, or making sure the test is meant for that product. You want to also make sure that you're aware of the product, the tester itself, the output capacity of the tester. Is it able to output 100 milliamps of current? Is it able to output 5,000 volts of voltage? So you want to be able to know what the tester is able to output too, and also let the operators know the inherent capacity of the tester. Few more things here that you want to make sure you don't defeat any ground protective circuits. Like I said, the ground pin, make sure that on the tester is plugged in, and do not use extension cords that have broken ground pins to make sure the product or the tester itself is electrically safe and sound. A few other things: no ESD smocks, no ESD grounding cables, shoes, or anything to be used around high pot testing. You will provide a path to ground in case if you come in contact with the product and the test. A few more things: do not use any non-approved accessories that are not approved by the manufacturer. This is to avoid any miscommunication or misinterpretation of what the instrument could do, and you're hooking up extra relays and things like that. They're not meant to be used with this device. It could cause potential shock hazard. All right, so I'm going to open up for any general questions now, and if you do have any questions, do use the chat box, and I could answer them live. If not, we could always answer your questions in email if required. Any questions, Tony?
I think we're good for now. We've handled them on the chat, so I think we're good.
Okay. All right. Thanks you. Resources, like I mentioned earlier, if you have operators, if you want a copy of this presentation, if you want a copy of any other previous presentation, we have it available. We're here to ensure we're manufacturers of high pot equipment, but we want to ensure that you're performing these tests properly, you're performing the test according to your standards that you're supposed to, and you're also keeping your operators safe. So we have all these resources available. The link is posted here. We could also post a link in the chat box if you like. But the webinars are available on our website. There's white papers available on our website. Any contact information you may need for us to contact us is available on our website. We do have our next webinar is going to be in April. So April 13th, again, it's on Wednesday, same time. This is going to be going into more details now about the high pot testing and the circuit itself. So electrical safety testing, how it's related to the actual circuits, and how we use our equipment to be able to detect different types of failures in a high pot testing or any electrical safety testing. I do want to point out a new service that we're starting to offer now is the application consulting program. If you went through the webinars, if you still had extra questions, and if you want us to set up a program where we could do an online demo of performing high pot tests on your products, or safely doing a safe workstation for your operators, or doing any kind of consulting service that you may require to go get up and running properly to run your high pot test, we offer services, consulting service packages. And here's the information for you you could email us at application@arisafety.com with your questions, or you could use the phone number listed here to contact us. The consulting page is also available on our website at arisafety.com, and there's a tab for consulting. Again, we also provide validation service if required to validate your setup is properly done. We also do safety standards analysis to make sure you're performing all the proper electrical safety tests that are required by your standards. Okay, that concludes our webinar for today. Here's our, if you have any questions, if you'd like a copy of the presentation, please do reach out to Brittany Socha, her email address listed here, or just visit our website and you can contact us, any of us, for any further information. Thanks everybody, and see you next time.